Next, we have a speaker from the industry and also from the consultancy, but not consultancy. But at the same time, still one of us in a sense, because Meil actually graduates from CASE. So Doug was a strong driving force for big data. He's a co-founder of the Explorers, a company that is based in Cleveland and has just been recently acquired by IBM. And so he has been doing a lot of software engineering, 20 years or so. And he's been a strong also proponent of big data dissemination across the US. And he's also the coordinator for the Cleveland meetup for Big Data project. And he's going to talk about big data and how it affects us in all facets of our lives. And with that, I'd like us to welcome Doug Meil.
Hi, I'm Doug Meil. Like Adrian said, I'm the co-founder and chief software architect at Explorers. We got acquired by IBM last year. We're part of the Watson Health division. I also was a very active HBase committer. Apache HBase is a distributed key value store for about 2010 to 2013. And like Adrian said, I also run the Cleveland Big Data user group, and we in fact had a meetup at CASE in January. How many people hit that meetup? A couple. Good, excellent, thank you. And it's something I'd also like to make sure that we get back here at least once a year. So we meet 6 times a year. So if you don't know about that meetup, please check it out. So what I'm going to talk to today is big data. Oh boy, it's a typo there. Big data management and its limitations. It's something you don't see the typos until you hit send. So I, in the course of doing business as well as also in the user community, Dr. Craig, your presentation was terrific. I have a lot of the same questions. People say, what is big data? Do I have big data? Is my data big enough? You know, I mean, it gets into a lot of personal questions. And so a lot of times I'm trying to either allay fears or explain concepts. And so what I'm going to do is talk about, not Explorers specifically, but some of the decisions that people may need to make in terms of recognizing problems and patterns, and where you may bump your head in traditional single node processing systems and some options. So how did I get here? This slide works well with an older crowd, people that are 80s aware. Anyone? Never mind. I did this to an undergraduate presentation last month, and I got stone cold silence. It made me feel very old. So you got to, this is my own personal opinion. It actually matches very well with what Dr. Craig said. I don't like to define big data narrowly in terms of, you know, it's got to be this, it's got to be the 4 C's, 5 V's, whatever. Very similarly, you've got either more data that can be stored on a single server in a cost-effective manner, or there's more data that can be processed on a single server with your required timelines, and these are related problems. If you trip either one of these tripwires, you have a distributed systems problem, and you're in the, for all intents and purposes, in the big data space. And one note on that is I have actually had conversations with people telling me that something is not big data. Like, okay, whatever. So let's look at weblogs. Weblogs is like the canonical big data processing example, right? Most people are familiar with web servers. Most people are familiar with the fact that they spit out a lot of logs. So one of the stats I heard from the very first Hadoop world back in 2009 was Facebook at the time was generating like 6 or 7 terabytes of compressed log data a day. They were smaller then, but even still, that's a heck of a lot of log data in compressed form. So there's actually 2 problems, and the second one is not obvious. The first one is just where do you put it? And so you need a place to stick all that stuff. And yes, storage is getting cheaper, but the harder problem is, can you read that off the disk fast enough to do something with it before the next set of data arrives the next day. And that's the harder problem. And that's where the storage and compute, that's where they intersect. Because if it was just about storage, we'd all be using Gluster clusters, right? But it's not just enough to put your stuff somewhere. You need to do something with it. I recognize that Hadoop is not the only distributed processing framework, but this is at least the reference that I'll be using for the slides. And never underestimate the power of oops, right? So in classic models, in classic processing models, I get data in, I do something with it, it's perfect, I throw the original away because I don't have the space to store it, and then hopefully I never have to go back and reprocess it. With distributed processing systems, you have to embrace that power of oops. You have to recognize you probably will screw it up. Or you'll just learn something more about the patterns that you wanted to analyze and go back for a deeper dive on some things. So maybe you got 80% of the patterns from a document. Maybe the next time you process it, you got 90 or 95%. Or maybe you thought you were done and you realize you're not. So it's an evolutionary process. Even data that you touched once, frequently you go back and take another look at. So here's a question for the room. Is 50 gigs big data? And you're supposed to say, no, it's not, because this is something that now you can buy a couple of flash drives and stick it in your pocket, right? So these are some Jeopardy stats. Last November, I had one of the people who worked on the Jeopardy project do a guest talk at the Cleveland Big Data, and so these are some public stats from the document. So it doesn't sound like much. So almost 7 million documents, but they had to divide it into, many, dozens and dozens of shards to index properly. They generated way more data than they actually received initially. They added in even more insights, and so you wind up with a factor of 10 on your input size. So first, yes, you have to find a place to put that, and then, oh, by the way, we want the responses from these indexes to be within a second. So that absolutely turned out to be a big data, a distributed processing problem. It wasn't Hadoop, but it was very much a distributed problem. And so don't judge the compute complexity just by the data size. Very similarly, you'll find that with machine learning algorithms as well. Spark getting more and more popular. You'll wind up with 50, 100 gigs, maybe still doesn't sound like that much in 2016 storage era, but you can have jobs that can run for hours and hours and hours because of algorithmic complexity. I just said that. Okay. Processing concerns sometimes dwarf the storage concerns. So let's talk about big data and limits. So where might you stub your toe or bump your head on a single system? And then we'll get into some framework options. So this is a typical Hadoop node spec. Dual CPU, 32 virtual cores, 120 gigs of memory, 8 2-terabyte drives, and a 10 gig network card. So how could we make it more awesome? So, compared to 5-10 years ago, that's still a heck of a lot of computing power, but it's still finite resources. So you can, depending on which problem you're trying to solve, you've got some knobs to turn to get more out of a single server spec. But they all come, they all come at a price, right? You're making compromises every step of the way. One option is I have a lot of data and I just want to get it faster, right? So you could go SSD, but you're going to lose storage capacity and you're going to pay more, which is not. Does anybody have infinite resources? No? Damn. Okay, so if you had an infinite checkbook, sure, you could trick out every server that you own with SSDs, but usually we're all balancing some budget and some operational constraints for whether you've got scientific users or whether you've got business or medical users. So for those that saw the Bloomberg talk in January that we had here, Bloomberg tricked out their Hadoop nodes all SSDs. Why? Well, they had a particular problem they were trying to solve. They were optimizing on low latency reads for whatever financial applications they had. And they actually described themselves as a medium data company. But they need that medium data extremely fast. So for them, that was the design choice that worked. Does that mean that everybody should do that? No. So the big data solutions tend to be problem specific. It gets back to the same thing Dr. Craig said, which is, what are you trying to do? So SSDs are an option for certain problems, but that's not a panacea. You can add more disks, right? We can add more spindles and fatter drives. If I have a 2 terabyte drive, why not go 4, right? 4 is better than 2. The problem is can you read it off the disk fast enough, right? So even with, and this is an old statistic but a goodie, a 1 terabyte drive with 100 megabyte transfer speed is going to take 2.5 hours to read completely. So if your processing case is continually doing deep indexing, machine learning over lots of data, I hope you're not running this on a single drive. Yes, you can store a lot, but you might be waiting a while to do something with it. So that's a place to bump your head. Really big disks, aka SAN, is really just another version of the fatter disks. Yes, you can store it, but you still have to consider where your compute is going to take place. Then you also have the relationships between knobs, right? Especially for RDBMS applications, at least for web commerce or things like that. You've got a relationship between storage and memory, right? So most RDBMSs usually have a 10x or 20x ratio of where things are fast. You can only effectively serve about 10 or 20x memory to storage if you're at least optimizing on low latency reads, which is usually what RDBMSs are geared for. You also have the relationship between the storage and CPU, right? So you're trying to balance a lot of things. Oh, and also, by the way, you're also trying to balance cost in here as well. So having a lot of cores is great, but if you need a lot of I/O and you've got more cores and spindles, that means you're not reading things fast enough. If you have more spindles and cores, that means you've got machines that are basically waiting instructions to get the data. So a lot of things to keep in mind. So let's talk about getting back to what are you trying to do? So your big data and framework options. So first, there's some design considerations. Oops, wait, that's one section ahead. Sorry, let's go back to the disks. So a central tenet of Hadoop is what they call a JBOD configuration, just a bunch of disks. So you guys are smart, you can read the statistics. So if you divide the data up, more servers, more spindles, you can read that same 1 terabyte amount of data in 2 minutes if you divide it across 100 drives. So that, in a nutshell, is what Hadoop is trying to do, either in terms of cores or in terms of spindles, is get more cores and spindles into the mix. And once you say that, beyond a single machine, you have a distributed system, which things get more complicated. You have more power, but things get more complicated. So let's look out for choke points. I see this all the time. Let's say that you do a cluster. You have some analytic substrate. You've got 50 nodes that you're whirring away on, and then you try to publish that somewhere. That little blue box is going to get hammered. Likewise, if you're processing, your Hadoop substrate is reading from something, that is one of the most common mistakes is Hadoop makes an awesome distributed denial of service attack vector for any of your network sources. So just be aware of when you're going from many nodes, writing to a single, or reading from a single node. So you usually, once you're going on a distributed substrate, you want to stay on some kind of a distributed substrate. So now let's get into frameworks and decision points. So getting back to what are you trying to do? These are the questions that I would recommend people thinking about. Does your data change? and a 50-cent word, immutable. You can impress your friends. We all know what that word is, right? This is word case. So if your data doesn't change, that makes it a little bit easier for you. There may be processing cases where you're just getting periodic dumps of a lot of data and then you are analyzing that. If your data does change, we'll get to that. What shape is your data? And I'll explain that. How fast do you need it? There's a huge difference between something that needs to be 1/10 of a second or less and I need it in about a second. These seem like they're the same problem. They are not even close. And then how many ways do you want to ask for it? What access paths do you have in your data? So these are things, irrespective of what technologies you end up choosing, these are the design principles that I would recommend people looking at. So does your data change? Files could be okay. There's a variety of file formats that you could choose, but files are okay. If your data does change, you do need some kind of a data store framework. Like HBase is one, it's not the only option, but you do need something that can handle mutations, because the next question that you have, if it's mutable, is, well, what was it before? And what was it before that? So you need something that can not just handle versioning, but also scale with as the data grows. So what shape is your data? The weblogs. Weblogs is a great simple example to explain to people, because a weblog is flat, right? It's 15 some attributes, and then the thing that people like to join in is some other demographic information about the IP address, and then voila, I'm a big data expert. Your data may not look like that. It may have nested structures. It may have nested structures of nested structures. I'm not here to tell you all the options, but I'm just saying you'd better understand what shape your data is and how many major entities or facts you have in your solution and the relationships you have between them. Because people see the weblog case and they go, I got it. It's easy, thank you. And then they'll come back 5 minutes later and go, oh, actually, we ended up having 20 facts that we needed to report on. And things get harder there. So how fast do you want it? If you need something in about a second in some kind of an ad hoc analytic query, there's a lot of SQL on Hadoop frameworks. It's not the only thing, but I'm just saying that's where you can basically do an IO drag race, throw a lot of servers, throw a lot of spinning disks, and if you have a lot of ad hoc users that are okay with, in a few second queries, there's a lot of frameworks that'll do that. If you need something that is like 1/10 of a second or less, you wind up getting back into that Bloomberg case of you have to look at everything, like how fast are the drives, you've got to put a lot of things in memory, you're going to need index structures even when you do those lookups. So you're going to need some kind of an index lookup, whether it's HBase Solr or something that's basically building out indexes for lookups. Guess what? That also takes more space. And you're going to have to buy more memory. So these are just things to look at. How many ways do you want to ask for it? So all of it all the time. That is a perfectly legitimate, it sounds ridiculous, but it's a perfectly legitimate case for batch processing. That is not going away. There is always going to be a case for all of it all the time. Some of it all the time, which is basically your ad hoc analytic user going, I'll look at a couple of these facts. And so there you're going to need something that can handle some dynamic predicates, some kind of like this, then this, and not this. And I'm not sure, ask me again in a few minutes. Oh, that's definitely the ad hoc case, plus also some search engines like Solr. So some of it all the time. Sorry, that was what I meant was there was like a fixed number of access paths. Sorry, that middle one should have been. There's 4 ways that I know that I'm always going to get this data because of my particular use case. The last one is the ad hoc one. My bad. And if you take a look, the middle one is like we're all familiar with Facebook, right? Facebook uses Apache HBase for the store of what you see on that page. There's a finite amount of access paths that you can see those messages, right? Is me and who I sent it to, and this and that, and then the time order, and that's kind of it, right? Now there's a ton of data. So it's a crazy amount of data, but they have a relatively finite amount of access paths for an outrageous amount of data. And so they're in the middle case. So they have a data structure that can scale many machines, but they have custom structures for a very set amount of access paths. Your typical back-end analytic user, that's in the last case, where it could be anything. And you're definitely not going to be promising 1/10 of a second response time on that last one. So files. I'm not sure if how many people are familiar, but there's different file formats. This is not comprehensive. But for people that aren't familiar with it, there are row-oriented serializations. Avro is one of the more popular ones in the Hadoop community that can expose binary serialized data, but with a schema, so it can be used very easily with other third-party and other open source tools like Hive and Pig and things like that. So you're not embedding that parsing logic of column by column into every other using framework. There's also columnar-oriented formats. So this is something that's usually new to the undergraduates. So like columnar format, what's that? It's an analytic framework. Parquet is one of the more common ones. ORC files, the other big one in the Hadoop space. These are more expensive to write and create, but they're optimized for read speed. So again, it's the right tool for the right job. Is Parquet the right file format for every use? No, it's an analytic format. But if you have a large projection of data that you generated some analytic file of a couple hundred columns, but your read case is only 10 or 20 at a time, why pay the price of throwing away 90% of the other data in that row? So that's what columnar formats are intended to do. And then CSVs, they're never going away. SQL on Hadoop frameworks, Hive, there's no shortage of them. You can Hive, Impala, Big SQL, Spark SQL, Drill. These tend to be I/O drag races. They don't tend to have indexes built in, but they're about basically providing, again, reasonably complex analytic functionality in some SQL-ish language with dynamic predicates. And these are not OLTP frameworks. But they're great frameworks for exposing a lot of data in ad hoc form where you don't have to be a programmer to go in and use them. Data stores, Apache HBase, this is the one I worked on for many years. It's a distributed key value data store. It's not a database. So it throws a lot of the fancy things away. So how many people are familiar with Berkeley DB? Anybody? Good. So it's basically, think of it like a distributed Berkeley DB. You've got a put, a get, a scan, and a delete. For all intents and purposes, that's what you do with this data. So you're designing your own keys. So it handles updates. It's got a block caching underneath the hood. It'll grow it'll grow across servers as the data grows. Pros are it's fast, it's scalable, and you have a high degree of data placement, and you can stick pretty much anything in there. One of the cons is you can stick pretty much anything in there, which means the serialization is up to you. So row key construction is an absolute art. But again, if you're already talking about dozens and dozens and hundreds of nodes, you kind of realize that you're going to wind up having to create something that's probably going to be crafted for your solution. Apache Solr, another popular framework in the big data space, supporting text analytics, text searching. This near that. The beginning of this word near that. Parametric searching. This greater than. This greater than that. And or again with complex predicates. Basically is a framework on top of Apache Lucene, which is an indexing framework. And it also can be served from Hadoop clusters as well, just like HBase. It can be updated. It's not meant to be a primary data store. This is meant to be a low latency and complex searching data store. So one of the common patterns is taking your raw data and then loading that into Solr for either end user searching or for application searching. And then don't forget, kind of like in the Jeopardy case, there's no free lunch. So your input size may be 50, 100 gigs. You're going to wind up with more than that after you load it into Lucene and Solr. But that's okay, because the problem you're trying to solve is I want fast access on this large amount of data. So those are the trade-offs. There's no free lunch. And that was pretty much what I had to say. Were there any questions? All right. Well, thank you for the opportunity for speaking.